Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. In this part, we're going to look at some of the applications of spin and antimatter, both in fundamental science, technology, and aspects of everyday life. This part of the lecture is just going to be an overview of how many of the things that we've discussed in the previous parts come together in practical applications. So we introduced the Pauli matrices previously, and it turns out these constitute the most widely used representation of spin. So in other words, for spin 1/2 particle, the spin operator can be written in this way. This amounts, you might say, to a specific choice of the alpha and beta that are in Dirac's papers, and indeed the alphas and betas for the three-dimensional system are constructed using these Pauli matrices. And now, with this necessarily two-dimensional representation, we basically have a 2x2 basis that describes the spin states. And so in this basis, we identify this basis vector as a spin up, and this is spin down. And indeed, when we turn on magnetic fields, for example, we can see that with this choice of the Pauli matrix, this convention for the electrons makes sense. In fact, the direction of the angular momentum of the electron is up, and this one is down. By up and down, we mean the projection of S upon the third axis is either plus 1/2 or minus 1/2, or plus h bar over 2, or minus h bar over 2. So the important spin 1/2 particles are the electron, then various other massive particles, and the neutrino. These are all fermions, and so according to Wolfgang Pauli, they obey something called the exclusion principle, meaning that total wave function has to change sign under exchange of any two identical fermions. So the total wave function includes both space and spin parts, so it is useful to distinguish the symmetric and antisymmetric combinations of electron spin wave functions. So here, for example, we have let's say we have two electrons. So since their angular momenta are h bar over 2, the sum of the two angular momenta can be 0 or 1. For the state 0, here's the linear combination of the two electron spin functions that gives a net angular momentum of 0, and then there's for the states that have total angular momentum 1, here are the combined functions. And so this one is called a singlet because there's only one. This is called a triplet because there's 3. And this structure is found in a pervasive way. For example, let's just have a look at a topic of recent interest. Has been the world's most accurate clock. I think that's changed slightly. It's still among the world's most accurate. This aluminum-ion logic-enabled atomic clock developed by David Wineland's group in Boulder. And so here are the various energy levels that are involved in the operation of this clock. And the group in blue are spin triplets. They can be identified as spin triplets. And then this one is a spin singlet. And then when you turn on magnetic fields, you have possible nuclear spins that can affect the overall angular momentum. But by and large, this classification of overall total spin is very useful in the design and operation of atomic clocks. Magnetism. Ferromagnetism, or the existence of permanent magnets, typically associated with elements that have many spin parallel electrons. So let's say iron has 6 electrons in the so-called 3D orbital, and so that enables them to largely line up. And so in the ground state of iron, you have net magnetic moment of 2 Bohr magnetons. So iron is, of course, very commonly used magnetic material. Neodymium is the basis of the ultra-hard magnets, one of which is shown in the magnetic levitation demo that you can see in the additional materials. Again, that's based on the fact that it has an F shell that can hold up to 14 electrons, and so you get the ground state in neodymium has 4 parallel spins, creating a large permanent magnetic moment. Most magnetic atom in the periodic table is gadolinium, which has 8 electron spins lined up. So the foundations of magnetism are based on electron spin. There's an emerging technology. Well, it's really an emerging science still. I mean, it has yet to yield a wide range of practical devices, but the read heads on modern magnetic storage media are due to a phenomenon called giant magnetoresistance, which involves the control of electrical current by magnetic techniques. So it makes it possible for very high density magnetic storage. And spintronics refers to the search for an alternative to electronic charge as a carrier of current in solids. There's a nice recent review of this spintronics field by Sam Bader and Stuart Parkin, 2 of the leaders, experimental leaders. And the foundational device for this spintronics is something called the dotted DOS transistor, hypothesized 24 years ago. It's still a subject of active search. It's something that seems to be hard to implement for various reasons, but there's very active research on this, the use of spin as a replacement for charge. Antimatter, again, is something that no one knew about or really even imagined prior to the Dirac equation, and it is a somewhat exotic sort of matter, but it is widely used. Positron emission tomography is a medical diagnostic procedure. Several million positron emission tomographs are taken of medical patients in the United States every year. Positrons are often used in synchrotron light sources because they have a longer lifetime in an electron storage ring. And there are various types of analytical techniques, for example, for finding voids and defects in materials. There's various types of positronium spectroscopy that have been developed. So these seemingly arcane and minor features that are found really only in the Dirac equation, are first revealed there, turn out to have a significant impact even in daily life. So that concludes this lecture. Hope to see you again.